All right, day 2 of probability. Our first thing we're going to do is a distinction between the types of probability we did yesterday and the types of probability we're doing today. Yesterday's probabilities were known as classical or classic or theoretical probabilities. Okay, unlike classic theoretical probability, which is associated with a well-defined total number of possible outcomes in an experiment, empirical probability, which is also known as experimental probability, is associated with a total number of possible outcomes that may vary depending on the experiment under consideration and the number of experimental trials attempted. So the probability of some event I is the number of times that occurred in the past divided by the total number of observations. So we're basing our probability off what was actually done in terms of an experiment or a survey, or something along those lines, as opposed to what should happen in theory. So, quick little example that illustrates the difference between that, or those things. Amanda used a standard deck of 52 cards and selected a card at random. She recorded the suit of the card she picked, then replaced the card. The results are shown in the table below. So, based on her results, what's the experimental probability of choosing a heart? Well, she got a heart 9 times out of a total of 30 trials. So her experimental probability was a 9 out of 30, which is 0.3. Now, 2, what is the theoretical probability of selecting a heart? Well, that's a type of question that we did yesterday. The theoretical probability of picking a heart would be, little typo there, 13 out of 25. Or there's a 1/4 chance of picking a heart. Number 3, based on her results, what is the experimental probability of selecting a diamond or a spade? So if you add up the number of diamonds to the number of spades, for a grand total of 18 of the 30 for an experimental probability or empirical probability, they mean the same thing, of 0.6. The theoretical probability of picking a diamond or a spade, well, diamonds and spades, those are mutually exclusive. So a 13 out of 52 plus a 13 out of 52 chance, 26 out of 52 are a 0.5 chance. So what we have in the probability world is an interesting connection between the experimental probability and the theoretical probability, which is the next thing we're going to talk about, law of large numbers. Let's see if we can zoom this a little bit better. Theoretical and experimental probabilities are linked by the law of large numbers. This law states that if an experiment is repeated numerous times, the experimental probability of an outcome will tend to be close to the theoretical probability of that outcome. The experimental probability is the quotient of the number of times an outcome occurs divided by the number of times the experiment was performed. When a fair die is tossed, the likelihood that the number on the top face of the die will be 2 is 1 out of 6 because only one of the 6 numbers on the die is a 2. So the theoretical probability of rolling a 2 is 1 out of 6, or about 17%. If a die is tossed 6 times, a 2 may be rolled more than once or not at all. Hence, the percentage of times that a 2 is rolled will vary from the theoretical probability of 1 out of 6. However, if the die is tossed 600 times, the relative frequency should come closer to approximating the theoretical probability. Hence, the number of times the result is 2 after 600 tosses should be fairly close to 100. So the more times you do an experiment, the closer your experimental probability will be to the theoretical probability. Another example that's often used to illustrate this is flipping a coin. If you flip a coin, 50-50 chance of getting heads versus tails. Now, if you flip it 10 times, you may get 5 heads, 5 tails, but not necessarily. If you flip it 100 times, 1,000 times, 1,000,000 times, the more and more times you repeat that experiment, the closer you'll get to that 50-50 breakdown of heads versus tails. And a common misconception, going to a coin example, if a coin is flipped once and it lands heads up, does that mean it will land tails up next time? Because the theoretical probability would say that if you're going to flip it twice, 50-50 chance, 1 heads, 1 tails. Okay, certainly not. The law of large numbers does not apply to any individual flip of the coin, but rather to the long run behavior. If a coin landed heads up 9 times in a row, it cannot be assured that the next flip will show tails. The probability that the next flip of the coin will be heads is still 50%, even if many more heads than tails have been flipped initially. It should not be expected that heads will appear less often in the future. So another way that this is sometimes described is it has no memory. No matter how many times you flip the coin, assuming it's fair, there's always going to be a 50-50 chance. What happened in the past has no impact on what the next flip is going to be. All the events are independent of each other. All right, next type of probability we're going to look at is working off of two-way tables. All right, two-way tables take a group of things or a group of people and classify them 2 different ways. So for this particular example, we have a medical facility, and there's a total of 13 people, and we're breaking them down by gender, female versus male, breaking them down by whether they're a nurse or a physician. So there are a total of 8 nurses, 7 of which are female, 1 male. There are a total of 5 physicians, 3 of which are physicians. Start that over. 5 total physicians, 3 of whom are female, 2 are male. Okay, so if you add down this way, the 7 plus the 3 is a 10, the 1 plus the 2 is the 3, 7 plus 1 is 8, 3 plus 2 is 5, and then the 10 plus 3 and the 8 plus 5 give us the 13. So what it's asking us to do with this information, the table below gives the staff breakdown at a local medical facility. If one staff person is selected at random, find the following probabilities. Okay, what's the probability that the person is male? Well, there is a 3 out of 13 chance of the person you chose, or the person that is chosen is a male. What's the probability the person is a physician? Well, 5 out of 13. Female and a physician. So that means you're both at the same time. So female and physician, 3 of the 13 people fit those both categories at the same time. Okay, female or nurse. So this goes back to one of the rules that we learned yesterday. We have 10 people that are females. We have 8 people that are nurses. Then we have to subtract off, well, what got counted twice, subtract off the and category, the people that are both nurses and females at the same time. So the 10 plus the 8 is 18. Take away what got counted twice, 11 out of 13 chance. All right, the next 2 examples are not actually covered in your textbook, but those are things you should know in this little corner of the math world, specifically on SATs. SATs have what are known as conditional probability problems. It's similar to a statement I made yesterday about level of difficulty. Those of you that had AP Stat or in AP Stat now, we did some rather challenging types of conditional probability problems. Okay, for what we need to know in this class, we're just looking at some basic table things here. What's the probability that the person is female given that the person is a nurse? So when you see that given that the person is a nurse, or sometimes they'll say it is known that the person is a nurse, is another common wording. What you do is you limit yourself to just that part of the table. So given that the person is a nurse means we only care about that row going across right there. So of those total 8 people, what's the probability that the person is female? So given that you're a nurse means you're limiting yourself to just that row, 7 out of 8 chance that you're a female. Okay, last one from this slide. What's the probability you're a physician given that you're a male? So given that you're a male means we're only looking at that one column going down like that. Limiting yourselves to just that column of the 3 total people in the column, 2 of them are physicians. So a 2 out of 3 chance you are a physician if you know that you are a male. All right, some more examples that have a little bit more going on here, but addressing the same ideas. At a public school system, the issue of dress code was brought up as a result of some apparent violations. 300 students categorized by gender were asked about their opinion on this issue. So our two-way table is breaking you down by gender, male versus female, and breaking down by your opinion on a dress code. You agree, you disagree, or you have no opinion. First question, what is the probability that a randomly selected student from these 300 will agree with the dress code or has no opinion? Well, agree and no opinion are mutually exclusive. We could just add those 2 individual probabilities together. 140 out of 300 plus 25 out of 300 gives you the 165 out of 300 chance that you will agree or you'll have no opinion. Second one, what is the probability that a randomly selected student from these 300 is female or will agree with the dress code? Well, female and agreeing with the dress code, they're not mutually exclusive. So we have to use the rule of adding up the 2 individual probabilities and then subtracting off what got counted twice. So the first part is the probability of being female, 180 out of 300. Second part, probability of agreeing with the dress code, 140 out of 300. And then we have to subtract off the both category, which means female and agreeing. That's subtracting off the 60 out of 300. So it gives us a final answer, 260 out of 300. All right, next one. What is the probability that a randomly selected student from these 300 students is male and will agree? Okay, male and agree, 80 of the 300 fit that category. Last 2 are the conditional probabilities. These are the ones that are not addressed in your textbook, but that you do need to know typically in most math classes that address working off of 2-way tables. Specifically, these questions are on the SATs. Okay, what is the probability that a randomly selected student has no opinion with the dress code given that the student is female? So given that the student is female means we only care about that one row going across. So of those 180 people, how many of those, I forgot what we're looking for, I'll have no opinion. So 15 out of the 180. Last problem from this slide. What is the probability that a randomly selected student is female given that the student has no opinion? So given that the student has no opinion means we're limiting ourselves to just those 25 people. So of those 25 people, what's the probability that the student is female? 15 out of the 25. So you see these 2 questions pair up where the top of the fraction is the same in both, but the bottom of the fraction varies. It's the given that changes between those 2 situations. So the order is important in terms of how they phrase that within the question. All right, last type of probability question we're going to be addressing. Okay, this is something that most textbooks refer to as hypergeometric probability. its name really isn't important. What is important is understanding when and how you're going to use it. This is something that is not emphasized in the AP Stat curriculum. Typically, we mention it briefly, but it's, to my knowledge, it's only appeared once as one part of one free response question in the last, 20 years or whatever of giving the AP Stat exam. So it's not something that's part of the curriculum. It's not something that's covered there. So those of you that are AP Stat students that don't remember this, it's probably because we just mentioned it briefly in passing. All right, anyway, on to the problems. Suppose we randomly select 5 cards without replacement from a standard deck of playing cards. What is the probability of getting exactly 2 hearts? All right, so we're talking about choosing a group of 5. So if we're choosing a group of 5 cards, the total number of ways that can occur is the 52 choose 5 on the bottom of the fraction. So those are all possible ways of getting a group of 5 cards from a standard deck. Now what's happening with these hypergeometric probabilities is we want some particular breakdown of categories in terms of, well, what are we getting with those 5 cards? So we're looking at the probability of getting exactly 2 hearts. So this left piece up top is going to represent all the different ways you could select those 2 hearts. There are 13 hearts, and we want 2 of them because that's part of the probability question. Now here is just not hearts. We don't care what other suit it is. For the purposes of this question, we only care about hearts versus not hearts. So there are 39 cards that are not hearts, and if we're looking at 5 total, and we want 2 of these, there must be 3 of those. So one of the things you can do to check to see if this is set up properly is that 13 plus 39 has to give you the 52. That 2 plus the 3 has to give you the 5. Because this is the total group of everything taken, and then the fraction up top breaks down the individual categories that are relevant to the problem. Okay, second example. A jar contains 40 marbles. 20 of them are fuchsia, 15 mauve, 5 lavender. 10 marbles are randomly chosen without replacement. Find a probability of getting 5 fuchsia, 3 mauve, 2 lavender. So the big picture here is from 40 marbles, we're choosing 10. So the bottom of the fraction, all the different ways that can occur. From a group of 40, we're picking 10, and we're doing it where the order doesn't matter. What order we pick them doesn't matter. Same as up top. I didn't specify that, but I should have. Now the breakdown for the categories up top are colors. So we have fuchsia, we have mauve, and we have lavender. So of the 20 fuchsia, we specifically want 5. Of the 15 mauve, we specifically want 3. Of the 5 lavender, we specifically want 2. And then once you have that set up, just make sure you get it typed in your calculator the right way in order to make the order of operations work out. All right, last example. Suppose 5 people are randomly selected without replacement from a population of 8 men and 6 women. Find a probability of at least 3 women in a group of 5. So at least 3 means we're talking about it could be 3 women, it could be 4 women, or it could be 5 women. So what we have to do is have 3 scenarios set up like we did up here, and then add them together. So the big picture is we have a grand total of 14 people we're choosing from. And from those 14 people, we're choosing a group of 5. So the bottom of the fraction is the 14C5, 14C5, 14C5. Then we're breaking it down, men versus women. So with 3 women, that means 3 women, 2 men. And then for the second fraction, 4 women is 4 women, 1 man. And then for the third fraction, all 5 women, no men. and that just becomes a rather tedious set of things to type in your calculator. There are no cool calculator shortcuts to bypass that. That just happens to be, it is what it is. Not so pleasant to type into your calculator. All right, there is one problem in tonight's homework that will address that. You need to know that for number 59 on page 410. And most likely will be one, at most two of those on the quiz on this stuff when we get to it later this week.